Something has shifted beneath the Atlantic, and the signals are no longer subtle. Measurements that once aligned cleanly with long-established models are now diverging in ways that are difficult to ignore. Risk maps that guided coastal planning for decades are being revised, not because of minor refinements, but because entire assumptions about how this region behaves are being reconsidered. The question is no longer whether the Atlantic holds hidden danger, but whether that danger has been underestimated all along. How does a system monitored for generations begin to produce results that no longer fit its own framework? Why are zones once categorized as moderate now edging toward high concern? And what does it mean when the most detailed models available begin to admit uncertainty rather than reduce it? When research into the Puerto Rico Trench first began, it was expected to reveal yet another case of theoretical geological risk, the kind that exists mainly on paper and rarely causes real concern. Instead, what emerged was something far more significant. At the bottom of the Atlantic Ocean lies a structure classified among the highest seismic hazard zones in the entire hemisphere. The update released in 2025 forced a recalibration of understanding, not because the trench had suddenly changed, but because the volume and precision of data finally caught up with the complexity of what had always been there. The deepest point in the Atlantic Ocean is not located in its center, nor far from land. It lies just north of an island with nearly 3.5 million inhabitants. This point, known as Milwaukee Deep, reaches a depth of 27,480 feet, equivalent to 8,376 meters. The scale is difficult to conceptualize. Even the tallest mountain on Earth could fit within that depth and remain submerged beneath more than 3,000 feet of water, or roughly 900 meters. This is not an isolated depression, but part of a much larger structure extending approximately 478 miles, or 770 kilometers, marking a boundary where the North American plate moves beneath the Caribbean plate. At first glance, that description resembles many subduction zones found across the globe. Yet this region does not behave in the same predictable manner observed elsewhere. Instead of a direct head-on convergence, the plates meet at an angle ranging between 10 and 20 degrees. This oblique interaction creates a network of faults that do not simply compress or descend, but slide, twist, and shift in multiple directions simultaneously. The result is a mechanical system that distributes stress unevenly, storing energy in ways that are far more complex than standard models typically account for. For decades, hazard assessments relied on simplified interpretations of this system. Faults were mapped based on limited data sets, seismic histories were reconstructed from incomplete records, and the overall behavior of the trench was approximated using analogs from more straightforward regions. These methods provided a workable framework, but one that assumed consistency where variability actually dominated. Between 2006 and 2024, more than 10,127 ground motion records were collected across the northeastern Caribbean. These measurements captured not only the magnitude of seismic activity, but also the way energy traveled through different geological structures. Subtle variations in wave propagation began to reveal inconsistencies with earlier assumptions. Areas previously thought to dissipate energy efficiently were found to amplify it under certain conditions. Fault segments once considered inactive showed signs of intermittent movement. The system, long treated as partially understood, began to appear far less predictable. The updated seismic hazard model released in 2025 did not simply refine earlier estimates, it redefined them. Regions within Puerto Rico now show a probability of ground shaking comparable to areas historically associated with major seismic risk. This comparison is not symbolic, but rooted in measurable parameters such as expected acceleration, frequency distribution, and recurrence intervals. The implications extend beyond a single island, affecting coastal regions across the broader North Atlantic basin. Beneath the ocean surface, high-resolution sonar mapping has revealed features that were previously invisible at this level of detail. Massive escarpments stretch across sections of the seafloor, some rising thousands of feet or several hundred meters above the surrounding terrain. These formations are not static. They are the remnants of ancient submarine landslides, events in which enormous volumes of sediment collapsed and moved downslope at high velocity. The scale of these past movements suggests that the conditions required to trigger them were once met and could be met again. The significance of these structures lies not only in their size, but in their instability. Sediment accumulation continues along the trench, gradually increasing the load on already steep slopes. When combined with seismic activity, even moderate disturbances could be sufficient to initiate new collapses. Unlike earthquakes, which release energy in waves, submarine landslides displace massive volumes of water directly, generating tsunamis that can propagate rapidly across ocean basins. Historical evidence supports this possibility. Geological records indicate that approximately 600 years ago, a powerful event generated a tsunami that reached distant shorelines. The magnitude of the earthquake associated with this event is estimated to have been at least 8.5, placing it among the most significant seismic occurrences in the region's history. Based on sediment analysis and recurrence modeling, events of this scale may occur within intervals ranging from 500 to 1,000 years. That range is not precise, but it places the present period within a window where such an event cannot be ruled out. More recent history reinforces the pattern of significant activity. In the late 18th century, a major earthquake estimated at magnitude 8.1 caused widespread damage across multiple islands. Over a century later, in 1918, another event measuring 7.3 triggered a tsunami that impacted Puerto Rico's northwest coast, resulting in 40 fatalities. In 1946, a magnitude 8.1 earthquake north of Hispaniola generated a tsunami responsible for nearly 1,800 deaths. These events are separated by decades, yet they share a common origin within the same complex tectonic system. In January of 2020, a magnitude 6.4 earthquake struck southwestern Puerto Rico. While smaller than the historical events, it revealed important details about fault interactions within the region. The earthquake did not occur along the main trench, but within the island's internal fault network. Its aftershock sequence extended over an extended period, indicating that stress redistribution was occurring across multiple structures rather than being confined to a single fault line. Activity continued to be recorded into 2023, emphasizing that the system remains active on multiple levels simultaneously. Despite the growing volume of data, uncertainty remains a defining characteristic of the current understanding. Several quaternary faults within Puerto Rico have not been precisely located. Their existence is inferred from indirect evidence such as ground deformation patterns and seismic wave anomalies, but their exact geometry and behavior are not fully mapped. This lack of precision introduces variability into hazard assessments, as even small differences in fault orientation can significantly alter the distribution of seismic energy. At the same time, advancements in modeling have highlighted areas where risk may have been underestimated. Simulations conducted using updated datasets suggest that a worst-case tsunami scenario could produce waves reaching heights of 49 feet, approximately 15 meters, along sections of Puerto Rico's northern coast. Such waves would not move slowly or gradually. They would travel inland with considerable force, carrying debris and water across significant distances in a short period. These projections are not based on a single source of data, but on the integration of seismic records, seafloor mapping, sediment analysis, and historical accounts. Each dataset contributes a piece of the overall picture, yet none provides a complete view on its own. The challenge lies in reconciling these pieces into a coherent model that accurately reflects the system's behavior. What complicates matters further is the interaction between different types of hazards within the same region. Earthquakes, submarine landslides, and tsunamis are not independent events here. They are interconnected processes, each capable of triggering or amplifying the others. A seismic event could destabilize sediment layers, leading to a landslide. A landslide could generate a tsunami. A tsunami could then impact coastal infrastructure already weakened by ground shaking. This chain reaction effect increases the overall risk beyond what would be expected from any single hazard considered in isolation. The updated model acknowledges this complexity, but it also reveals its limitations. While it incorporates a far greater volume of data than previous versions, it still relies on assumptions where direct measurements are not available. In some areas, these assumptions are well supported. In others, they introduce uncertainty that cannot be fully resolved with current technology. One of the most notable shifts in the new assessment is the recognition that risk is not evenly distributed. Certain zones within the region show significantly higher probabilities of intense ground shaking. These zones are often located near intersections of multiple fault systems, where stress can accumulate more rapidly and be released more abruptly. Identifying these zones has become a priority, as they represent areas where even moderate events could produce disproportionately large impacts. As data continues to accumulate, patterns are beginning to emerge that were not visible before. Seismic activity appears to cluster in ways that suggest underlying structural controls rather than random distribution. Some zones experience repeated low-level activity, while others remain quiet for extended periods before producing larger events. This uneven distribution challenges the assumption that risk can be averaged across broad zones, reinforcing the need for more localized assessments. At the same time, the Atlantic itself is not a static environment. Oceanographic conditions, sediment transport, and even long-term climatic factors can influence the stability of the seafloor. Changes in sea level, for example, alter the pressure exerted on underwater slopes. While these changes occur gradually, their cumulative effect over decades can contribute to conditions that favor instability. The convergence of these factors has led to a growing recognition that existing maps may no longer provide an accurate representation of current risk levels. They were built on data sets that, while robust for their time, lack the resolution and scope now available. Updating these maps is not a simple process of adding new data points. It requires re-evaluating the underlying assumptions that guided their original construction. As the revised models take shape, they reveal a system that is both more complex and more dynamic than previously understood. Zones once considered peripheral are now being re-evaluated as potential points of concern. Zones thought to be relatively stable are showing signs of underlying activity. The overall picture is one of a region in which multiple factors interact in ways that are not fully predictable. This evolving understanding does not indicate that a major event is imminent. Rather, it highlights that the probability of such an event may be higher than earlier models suggested. The distinction is subtle but significant. It shifts the focus from whether an event will occur to how prepared systems are to respond if it does. Beneath the surface, the Atlantic continues to move, its structures adjusting incrementally over time. Each small shift contributes to a larger pattern, one that is only now beginning to be fully recognized. The data collected over the past 2 decades has not simplified this pattern. It has revealed its intricacy. And within that intricacy lies a question that remains unresolved, one that becomes more pressing as each new dataset is analyzed. If the models that guided understanding for over 20 years required such extensive revision, what else might still be missing from the current picture? Well, the answer to that question begins to take shape when the updated datasets are examined not as isolated improvements, but as a complete reconstruction of how the Atlantic margin is interpreted. The shift is not confined to a single trench or a single fault system. It reflects a broader realization that the interaction between tectonic plates in this region does not follow the simplified patterns that earlier models depended on. Instead, it behaves as a distributed system where stress is transferred across multiple structures, sometimes over distances of hundreds of miles or several hundred kilometers, without immediate release. One of the most important developments in the updated model is the recognition of what had previously been treated as background noise. Low-magnitude seismic activity, often dismissed as insignificant, now appears to play a more important role in understanding how stress accumulates. These smaller events, when mapped over time, reveal corridors of movement that align with previously unmapped or poorly defined faults. In effect, the system has been quietly outlining its own structure through repeated micro-movements, providing a level of detail that was not accessible before the expansion of monitoring networks. This pattern has been particularly evident along transitional zones between the main trench and the interior of the Caribbean plate. These areas do not experience the largest earthquakes, but they act as connectors, transferring stress between larger fault systems. When activity increases within these corridors, it can indicate that stress is being redistributed rather than released. That distinction is critical because redistribution can lead to accumulation in areas that are capable of producing far more powerful events. At the same time, advances in seafloor imaging have revealed that the geometry of the Puerto Rico Trench is far more irregular than previously understood. Instead of a continuous uniform boundary, it consists of segmented sections with varying degrees of curvature, depth, and structural composition. Some segments descend steeply, while others flatten out before dropping again. These variations affect how the North American plate moves beneath the Caribbean plate, creating points where movement can slow, lock, or accelerate. Where the plates lock, stress builds over extended periods. Where they move more freely, energy is released more gradually. The challenge lies in identifying which segments are currently locked and how long they have been accumulating stress. The updated model suggests that certain sections of the trench may have remained relatively quiet for longer than expected based on earlier recurrence estimates. This does not guarantee a large event, but it increases the possibility that one could occur if the accumulated stress exceeds the resistance of the fault. Further complicating the picture is the role of sediment layers along the trench. These layers, composed of fine materials deposited over thousands of years, act as both stabilizers and potential points of failure. In some cases, they absorb and distribute stress, reducing the likelihood of sudden movement. In others, they become saturated and unstable, increasing the risk of collapse. The distinction depends on factors such as thickness, composition, and the angle of the slope. Recent analysis indicates that certain zones along the trench contain sediment accumulations exceeding several thousand feet in thickness, or more than 1,000 meters. These massive deposits represent a significant mass that is constantly influenced by both tectonic movement and gravitational forces. When subjected to seismic shaking, even at moderate levels, they can lose cohesion and begin to move. Once initiated, such movement can accelerate rapidly, transforming into a large-scale submarine landslide. The risk associated with these landslides extends beyond their immediate area of occurrence. As they displace water, they generate waves that can travel outward in all directions. Unlike tsunamis generated by earthquakes, which often have a more predictable wave pattern, landslide-generated tsunamis can be highly irregular. Their wave heights can vary significantly depending on the volume and speed of the collapse, making them more difficult to model accurately. The updated hazard assessments incorporate these scenarios with greater detail than before. Simulations now account for variations in slope stability, sediment distribution, and potential triggering mechanisms. The results show that in certain cases, localized tsunamis could reach coastal areas faster than those generated by distant earthquakes. This reduced warning time presents an additional challenge for preparedness systems that rely on early detection and communication. Another element that has contributed to the reassessment of risk is the improvement in satellite-based measurement techniques. High-precision instruments are now capable of detecting subtle changes in surface elevation, sometimes on the order of fractions of an inch or a few millimeters. Over time, these measurements reveal patterns of deformation that correspond to movement beneath the surface. In Puerto Rico and surrounding regions, these patterns indicate that strain is accumulating in multiple directions, consistent with the oblique movement of the plates. This multi-directional strain is significant because it implies that stress is not confined to a single axis. Instead, it spreads across a network of faults, increasing the number of potential points where a rupture could initiate. In practical terms, this means that the exact location of a future large earthquake is more difficult to predict, even if the overall level of risk is better understood. The reliability of hazard maps depends on the ability to define both probability and location with reasonable accuracy. While the updated model improves the estimation of probability, it also highlights the limitations in pinpointing specific locations. This dual outcome is at the core of why existing maps are being reconsidered. They are not necessarily incorrect, but they are incomplete in ways that matter for planning and response. Infrastructure across affected regions has historically been designed based on earlier versions of these maps. Building codes, evacuation routes, and emergency response strategies all rely on assumptions about where and how hazards are most likely to occur. As those assumptions change, so too must the systems built upon them. The process of updating is gradual, but the recognition that it is necessary has become more widespread. Coastal zones face a particularly complex set of challenges. In addition to seismic risk, they must account for the potential impact of tsunamis both from earthquakes and from submarine landslides. Wave height, speed of arrival, and extent of inland flooding can vary widely depending on the source and conditions. The updated models attempt to capture this variability, but they also emphasize that no single scenario can represent all possibilities. If you found this clear and informative, take a moment to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience so more people can stay informed about what is happening beneath the Atlantic.